Welcome to lesson 1.6, problem solving by finding patterns and organized counting. So in this lesson, we're going to think about different ways that we can work at solving problems. We're going to look at finding some linear patterns. And then we're also going to do some organized counting, and I'll show you what that means later. So just a couple tips on problem solving. Step 1. Read the problem as often as you need to. One of the trickiest parts with word problems is the words. So making sure that you understand what's being asked is going to be really important. When I'm reading through word problems, I do a lot of either highlighting of the key parts, or I will underline key parts or circle them. But there's usually a whole lot of extra stuff. Step 2, decide what information is important and what isn't. So these two are totally linked together, right? So it's going to be that same type of thing. Read through it and highlight, underline, circle. Step 3, choose a strategy, a whole bunch of ones. It might be that you can write an index n. I know you don't know what that means yet, but this is going to be often coming up with a table, this use an index n thing, and then it will allow you to write an expression. We're going to be practicing that for sure. If they give you a formula, or if a formula exists, like things like speed, formulas exist for speed, it's distance over time, you could do that. Sometimes working backwards or trial and error is a good way to get an answer, but just a note that unfortunately this can't get you full marks on a test. But it would get you some, so never discount trial and error. Drawing a diagram sometimes often helps in certain problems where you're going to see more as we go through the year, or you can use organized counting, and we'll show that as well. Another thing which so many of us are reluctant to do is just pause. So sometimes you may panic and you feel like you're never going to solve the problem. But at this point, you just need to pause and remember some of the following. Think back if you can remember any problem that's similar, or you could go on to another problem and later come back to it because your subconscious will keep at it. Take a short break from math, go do something else for a bit and then come back. And also after a pause, you can talk it over with a classmate because two heads are better than one. So when you're problem solving, try something. I know for some of you, you don't even want to try unless you think you're going to get the right answer. But messing around, trying something out is going to be a good way to at least get started, to show a little bit of your understanding. And when you get your answer, check and see if it makes sense. So check your answer. Is it reasonable? Like if you're finding the weight of human people and you get something is 2,000 kilograms, that's not going to be a reasonable answer. And this one, so important. Did you answer the question that was asked? So often not often, always, if you are asked in math, if you're asked a question in words, you got to answer it in words. And that's going to tie into this last part, writing up a clear solution. So if asked in words, answer in words. That can be your final therefore statement. So your final therefore. Therefore is those 3 dots, remember? Therefore statement. And you also have to show your work. And lots of ways to do it. It could be a table, it could be some algebra, lots of different ways. So we're going to implement some of these strategies now. If we are finding a pattern, the diagrams show figures made from toothpicks. And they ask us if the pattern continues, how many toothpicks are needed for the 6th diagram? So I'm going to start by counting how many toothpicks we have in each one. So this first one has 4. Then this one has 4 plus another 3. So we're at 7. So 4, 7, plus another 3 is 10. And plus another 3 is 13. And so I've noticed that each time I move up, I'm going to be adding 3. So if I add another 3, then there'd be 16 toothpicks in the 5th diagram. And if I add another 3, 19 toothpicks in the 6th diagram. So what I've just done there, even though doesn't look like traditional supermathy, I've shown my work. I've shown how many it was for each one. And then with this plus 3 up here, I've shown what I was doing to get to my next numbers. So how many toothpicks? The question here was asking how many toothpicks are needed for the 6th diagram. Well, we figured it out. We're going to answer it in words. We would need 19 toothpicks for the 6th diagram. So in order to come up with an expression to describe this pattern, we're going to use this thing, an index called n, in order to find the relationship. So if we let n be what figure it is, so let n be the numbered figure. And by that, I mean, if you could see what I'll use a highlighter. So this is the first figure, this is the second figure, that's the third figure. So if n is the numbered figure, then I have a pattern that looks like this. N of 1, 2, 3, 4. So that's my figures. And this would be the number of toothpicks. It was 4, 7, 10, and 13. I'm going to show you this way because it'll work for everything moving forward. I hate when that happens, sorry. Each time we were going up by 3. So that means each time n increased, our actual value was going up by 3. So for our pattern, we're going to use this general, I'm going to show you a formula that works for any of these linear ones where you increase by the same amount each time. So our step, and this here was the step. So our, maybe I will write it in red. We're going to take our step, whatever the step number is, we're going to multiply that by n, and then we're going to put we're going to have to add some sort of correction though, because if you look, I'm going to highlight in bright yellow, when n equals 1, 3 times 1 would give us 3. We'd have to add 1 more to get 4. When n equals 3, 3 times n, or 3 times 3 is 9, plus 1 more is 10. So we'd have to do that plus 1 more each time. That number actually ends up being our value when n equals 0. And I'm going to show you what I mean. I'll use green. I think there's a way for me to highlight that and make it all go to green. Okay. So the value when n equals 0. For that, I would love for you to go backwards. So when n equals 0, instead of adding 3 to step up like those red arrows, I'm going to subtract 3. So 4 subtract 3 is 1. Oh, I went back too far. This should be green. So in this particular question, our pattern is going to equal the step, which was plus 3 times n, and then I'm going to have to add my original when n equals 0, and I'm going to get this final expression for the pattern. So if I wanted to find out how many toothpicks I would need on the 100th diagram, I would let n equal 100, and so my pattern would equal 3 times 100 plus 1, which would be 301 toothpicks. So it's going to be useful that way. Question 2. The first 4 numbers in a pattern are 60, 57, and 54. If the pattern continues, what's the 7th number? So I'm going to make one of those tables again. So n, and then I'm going to have 1, 2, 3, 4, 5, 6, 7. And my first numbers were 60, 57, 54, 51. And I'm going to look and see, and I notice that each time my step, I should have these in red so it's consistent. Each time I'm going down by 3. So if I were to continue this down by 3 each time, I would get 51 minus 3 is 48, minus 3 is 45, minus 3 is 42. So just by not even coming up with the actual pattern, I could figure out that the 7th number would be 42. So therefore, the 7th number in the pattern is 42. Find an expression. So this is where we're going to do that thing with n. And we're going to use the thing where it's pattern equals step times n plus the value when n equals 0. So our pattern is going to equal our step, which is minus 3 times n. And then we're going to add the value when n equals 0. So to find the value when n equals 0, instead of subtracting 3, because I'm going backwards, I'd have to add 3. It would mean that I'd have to start at 63. And one way for us to check whether if this is right, I'm going to let n equal 7 and check if pattern equals 42. So that would be minus 3 times 7 plus 63, which would be minus 21 plus 63, which happens to equal 42. So that means that I'm pretty confident that this pattern, the expression is the right one for the pattern. And then we've got some classwork that we're going to work on together for this problem. But now I'm going to show you a little bit of organized counting. So if we have 6 sticks of lengths 3, 4, 6, 7, 10, and 12, how many different triangles can you form using any of these sticks? This one's actually a pretty tricky question. If you just try and think without drawing pictures and start being organized counting. So I'm going to be forming triangles. That's the key part here. And I can only use 3 sticks at a time. And I can't repeat a stick, right? Because that wouldn't make sense. So I'm going to start with a base of 12. If I had a base of 12 centimeters, what 2 sticks could I possibly have to make a triangle? And then I'm going to go down to the next longest one, which is 10. So if I had a length of 10, what options would I have to make a triangle? Well, I could definitely have 7, and I could have 6, and I could have 4, and I could have 3. They will all work. And by work, I mean if we had a length that was only 1 centimeter long, there's no way I could make a triangle out of it, because 10 centimeters plus 1 centimeter, there's no way I could get as long as 12 centimeters. But for 7, 6, 4, and 3, that would work. And then I'm going to go down and look at the other bases. So that was with 12 and 10. If I have 12 and 7, now I'm not going to include 10 again, because I already did a triangle with 12 and 12 and 10 and 7. But I could do 12 and 7 and 6. That would work. 12 and 7 and 4. If I made this one 4, 7 plus 4 is only 11. There's no way that would work. So with 12 and 7 and 6, I only have, so this gave me 4 triangles. This gives me another triangle. That's it for 12 and 7 and 6. If I look at 12, oops, green, and 6, so if that one's 6, well, I've already done 12, 6, 10, and I've done 12, 6, 7. What about 12, 6, 4? If I do 12, 6, 4, they're never going to meet. So there's no more ones that have a base of 12. So that's what I mean about being organized and methodical. And if we go through this then for all the ones with 10 and 7 and 6 and 4 as the bases, you can work your way through. And we'll finish this one in class to see what you can do. Questions 2 and 3 we're also going to do in class because I think it's going to be really important for you guys to try without me showing you anything about them. So thanks for watching. That's the last lesson in this unit. And next we'll be getting ready for our assessment. Bye.